You may remember that when we talked about transition delay faults, when we talked about scan testing, so this is my scan. Sorry. Okay. So these are my Q1, Q2, Q3, D3, D2, D1. Okay. And this is the normal mode capture. So we sometimes, this is also known as broadside. So if you are capturing the output of the D1, D2, D3 into these flip flops, we call it as a broadside load. If you are shifting this data from the scan in, it is known as narrow side load. Okay. So what I had mentioned to you was the scan clock, the rate at which we introduce the scan data into the scan chains, we cannot unfortunately bring it at the rated clock. Imagine that this is a 100 megahertz clock. So this circuit works at 100 megahertz. So unfortunately, I can't scan the data at 100 megahertz, because what will happen is when the circuit works at 100 megahertz, maybe the state will go from 000 to 01, something like this. Only one bit will change. But what could happen is the test vector generation tool may generate 000 as a test vector, and then that may result in the value being captured being 1, 1, 1 or something like that. And then when I start shifting the response, see, all the values will change from 0 to 1. Okay, this 1 will shift here. So all these guys are changing, every bit is changing. So during scan shift, a lot of activity may happen in the flops. So a lot of flops may be toggling. And if lot of flops toggle, lot of gates will also toggle, causing a lot of power dissipation. So if your circuit is rated at 100 megahertz, and if you try to shift in data at 100 megahertz into the scan chains, the power dissipation may be very, very high, more than what the rated power is. Okay, so scan test power may be many times the functional power. That means the package may melt. It generates so much heat that it will melt the package. It can happen because the person who designed the package, they designed it for functional power. But now we are sort of arbitrarily applying all kinds of zeros and ones, causing a lot of power dissipation and thereby melting the package. So we have to slow down the scan shift frequency. So that means slow down scan shift. So apply the scan test slowly. How slowly? It may be as less as 1 megahertz or 500 kilohertz or even less. Okay, so much slowly. It may be in like hundreds of kilohertz, half a megahertz. Okay, otherwise you will possibly destroy the chip. So going back to the transition delay fault model, this is my scan register. So V1 is shifted slowly. So that will initialize some zeros and ones into the scan register. The circuit will respond to these inputs, and when you do a capture, so this is, let us say, V1. Next we are going to do a capture here. This capture will launch the transition. Okay, so remember, we may have had a initialized this to 0 0 0 1, and when we capture, this may go from 0 to 1, this may go from 1 to 0, this may remain 0, this may remain 0, but in the process a transition was launched, and the new values will cause a propagation to one of these outputs, and the result of that is getting captured in. So initially this capture launches a transition, meaning V2 got applied, and then immediately then afterwards, right, we have to apply what is called as a fast transition. So this is the so this may be, let us say, a slow clock. We are applying V1 at a slow pace, V2 also was applied at the slow pace, but the result of the when the transition was launched, we had to wait only for a short time before we capture. Okay, we cannot wait for usual time. So normally we will go and do the next capture here, but that may not be correct. Okay, we launch the transition here, and let us say it's a 100 megahertz clock. So in 10 nanosecond itself, we have to bring in the next vector. So this will be 10 nanoseconds. How? Because see, we are looking for the rated speed of the circuit, right? We have to verify that the circuit works at the 10 nanoseconds clock. If you shift very slowly, then the circuit will work, no problem, because it doesn't have any fault as such, right? It has only a speed fault. If a circuit is too slow to rise, but you are applying a very slow clock, then there is no problem, isn't it? You can think of an analogy, right? So suppose the doctor wants to test your heart rate or something like that, okay, and he says you run, right, and then we'll measure the rate at which your heart is able to beat or something like that, right? See, in the normal mode, see, you don't really run so fast. The normal mode, you may not be a runner at all. You just walk. You may be a slow walker. We are worried that you have a speed issue. That means you are not able to run at a certain speed. That is what we are trying to test. So the doctor asks you to run at that particular speed. Then you can measure the heart rate and decide whether you have a problem or you don't have a problem. But suppose the doctor says run slowly or walk, right? You will not have any problem. You will happily go and pass the test. So the transition delay fault testing presents a challenge because we apply clocks very slowly in scan. Okay, we apply the clocks much slower than the functional clock, right? The functional clock may be a 100 megahertz clock, but we may be applying it at 500 kilohertz or 50 kilohertz or something like that. So we should not use the so we cannot say, hey, bring in the V1 here, then by capturing bring in V2, and then give it sufficient time and then capture. Of course, it will have no speed issues because this is a very big clock. After doing the transition, we should bring in the next clock here. This is the actual period of the clock. So we have to modify the clock waveform. Okay, so clock waveform will need to be modified. for transition delay fault. So, that is one of the challenges. And whether we can apply the vectors in such a way that the transition gets launched and gets propagated to one of the flops, that is not always, it's not very clear whether it can be done or not. Okay. So, tools try to set V1 and V2 such that V2 can be generated by capturing the response of V1. In other words, V2 is nothing but response of V1. Can it be, can we always create such V2? May or may not be possible. So, this method of applying vectors for transition delay fault is known as launch off capture. So, if you see the scan shift, see there is a scan enable signal, right, which dictates whether the scan is being, the register is being used as a shift register or as a parallel in parallel out register. See, that will remain high during this period when we are shifting. Then here it will go low. And again it will go high.